Welcome. I hope you're doing well. My name is Rania Boulahia. I have a master's degree in mathematics, and today I'm gonna be giving you lecture. It is the first lecture in Algebra 1 and Analysis 1. We already talked about logic and sets. Today we will talk about relations and maps. Relation. Binary relations. Let E be a non-empty set. A binary relation on E is a part of R of E times E if x, y are in E such that x, y are in R. We say that x is a relation with R, and we noted x relation R. So if this is E and this is by them, this area, let's taking an area in the E times E space. If we take two elements from that space, if they belong to that area R, we say that x and R are has a binary relation. Property of binary relation: let E be a set of R, a binary relation on E. R is reflexive. Reflexive means that every x has a relation with itself. So for all x in E, x relation x. R is symmetric. If x and y are in E, x relation y implies that y has a relation with x. Antisymmetric. If x and y are in E, x and R have a relation. X has a relation with y, and y has a relation with x. That means that x equals. That implies that x equals y. Transperative: if x, y, and z are in E, x relation y and y relation z, that implies that x relation z. Let's take an example for a binary relation. For example, if greater than or equals to in the space R, so every x is greater than or equals to x, every x is greater than y, that means y is greater than or equals to x. So this is very good example of a binary relation, and it is x is greater than or equals to y, and y is greater than or equals to x. That implies x and y are equals. It is also transperative, so greater than or equals to is a binary relation and have uh, the property reflexive, transperative, and antisymmetric. Equivalence relation. What do we mean by equivalence relation? The primary definition is let E and B is set and Y is a binary relation of E. We say that R is an equivalence relation on E if R is reflexive, symmetric, and transperative. So an equivalence relation is a binary relation that have the property reflexive, x, antisymmetric, which means x relation with y implies that y relation x. Transperative for x, y, z. X is relation with y and y is relation with z. That implies that x has a relation with z. Equivalence classes. Let R be an equivalence relation on a set E. For any x in E, the set clue x dot defined by clue of x equals y in E such that x in relation with y is called the equivalence class of x modulo R. The element x is called representative of class X. The set of equivalence classes is in E modulo R is denoted by X slash R, and it is called the quotient sets of E by R. E relation X equals class of E X, where X is in E. The quotient sets is a set of sets that have E relation with R is included in the P of E. P of E is the set where the set that is the element of the set are every set possible that we can generate it from E. Remark, let R be an equivalence relation on E. Using reflexivity, symmetry, and transitivity, we show that for all x and y in E, x relation with y is equivalent that class of x equals class of y. Therefore, any elements that belongs to class of x can be taken as a representative of class of Example, let n be a non-zero integer and p and q are in Z. We say that p is congruent to q modulo n, denoted p congruent to q modulo n. We studied this in this is high school level. If n divides p minus q, i.e. identically equivalent to Berger's k in Z, p minus q equals k times n. Questions. Show that congruent modulo n is equivalence relation on Z. Determine the equivalence class of P and Z. Determine the quotient sets Z and Z. Let E equals to Z times Z dot. Show that A and B relation A prime B prime equivalent to AB equals to A prime B is equivalent relation. So you can pause the video and try to solve this example. This is high school level. P is if Q equals to 0, if this Q equals to 0, that means that P is a multiplier of n. Not 0, this is the rest. Division, this is the rest. The rest that it's less than n. It's between 0 and n. Partial order relation. Let E be a set and R be a binary relation on E. We set R is a partial order of n if it is reflexive, antisymmetric, and transperative. Reflexive, X was relation with X, antisymmetric, which means X relation with Y and Y relation with X.